Okay, everyone, it's 9 o'clock. We'll go ahead and get started. I'm Tracy Vogler from Sandia National Laboratories, and our first speaker this morning is Charlie Knockley. Charlie did his PhD at Cornell. He joined Los Alamos, and then he moved a couple hours south to Sandia in 2007, spent a few years there in the ICF and radiation effects group before moving back to Los Alamos about 3 years ago, and now he leads the Theoretical Design Division at Los Alamos. So he's going to talk about stockpile stewardship. Charlie?
Thanks, Tracy. Well, let's see. It's a real pleasure to be here. Can everybody hear me okay? Yeah? Excellent. There's signs of life in the audience. It's a great pleasure for me to be here. I did my PhD, Tracy kindly didn't mention this, 20 years ago. So those 20 years have been spent entirely at two of the three defense laboratories. And there was nothing like this in 1996 when I completed my PhD. And it's really it's a tremendous pleasure to see such a great class of new scientists coming out and being supported by the DOE, by NNSA, with a view towards keeping that lifeline, keeping that fresh blood coming into the laboratories. That's really essential, you know. And when I look over the last 20 years, you know, in 1996, testing had just ended a few years before, and the stockpile stewardship program really was just ramping up. There were a couple years of free fall in there, right, where nobody really knew what was going on. Stockpile stewardship did not kick in really until a few years after testing, and so as a result, I've always noticed at the labs, there are not many people my age, as it turns out, because there was a real gap in hiring, and then there were a lot of retirements just before. And really, it was when stockpile stewardship kicked up that the pipeline started getting reestablished, and it's great to see this continuation of that pipeline. Let's see, so perfect. So let me tell you a little bit about what stockpile stewardship means from a nuclear weapons designer perspective. So that's the division I lead at Los Alamos, is the nuclear weapons design division at the laboratory. And we have quite a few responsibilities, and some of them are established, many of the main ones are established by statute. Here I show a picture of Secretary of Energy Ernie Moniz. I was amazed during the Iran negotiations to see people to hear, mostly because I'm a big podcast aficionado, listen to a lot of Slate podcasts, and all of a sudden they're talking about Ernie Moniz, you know, it's fantastic. And they're mostly talking about the role of the scientist in the Iran negotiations, which was very prominent, an unusually prominent role, and then talking about the hair, because they loved that on the podcast, you know. And you got to admit, you know, there it is. So the lab directors, all three laboratory directors each year write a letter. And that letter is the summary and is based on a tremendous amount of work at each of the laboratories, where they certify to the President through the Secretaries of Energy and Defense that the U.S. Nuclear weapons stockpile is safe, it's secure, and it's effective at accomplishing its missions, right? And it's a long letter, and it goes through in detail you know, what's the scientific basis on which that judgment rests. And that, in and of itself, is just the tip of a very large iceberg, right? The work, the science that goes on to support that is huge and is ongoing every day at all the laboratories. What is the objective of this program, the Stockpile Stewardship Program? And it's to maintain the certification of these weapons without conducting additional nuclear tests. People sometimes say, well, we do this without conducting nuclear tests. That's really not true. We have a huge basis, as I'm going to talk about later in the talk, of nuclear test data that's absolutely essential to what we do. But we have not conducted any additional nuclear tests since 1992. So that's going on 24 years now. At the time, I remember back again to when I joined the labs, there was tremendous debate over whether this was at all feasible to do, right? So it's been, and I think we should remind ourselves of this regularly, it's been a tremendous success for these past 20-some years to be able to do that at all. And previous generations of laboratory scientists were quite skeptical that this could be done at all. So how do you do such a thing, right? These weapons, as I'm going to talk about, operate in in regimes that are very far removed from anything we typically do in a laboratory, at least in a laboratory that you'd like to keep standing after the experiment. So how do you do that? Well, it's a combination. There's only three things in science anyway, right? There's theory, there's experiment, and then there's simulation. Those are the only three things. Those are the pillars, right? So you have to have strong efforts in all three of those pillars in order to carry out this mission. So the design laboratories and the production complex are essential to maintaining this deterrent. There's a wide variety of diverse array of weapons, and I've given you a list of them here. And they're gathered into these legs of the triad, as I'm sure you all know. There's the air-carried leg, there's the ICBM leg, and then there's the submarine-launched ballistic missile leg. And each leg of that triad offers complementary and reinforcing benefits. The triad was arrived at in the 1960s, and it's been looked at periodically by almost every administration that has come into to govern the U.S. since then, and every administration has reinforced that that really is still the way to go, and that's still what we have today. And we support several warheads on each leg of that triad. We have multiple aspects of this deterrent that we need to balance. And although while we're focused on the laboratories, and I myself as a born and bred laboratory citizen tend to focus on the laboratory, you also have to remember and to really learn to appreciate the production complex that is at the rest of the DOE sites that underwrites the deterrent. They have tremendous scientific problems as well, and many times the function of the laboratories is to provide some scientific backbone for the production complex to help them solve sometimes some very pragmatic problems. One of the things about this field is that you get problems that come up that you were never trained to deal with, right? So that's one thing I want to communicate to you guys. As you come, as I hope many of you will come into careers in the laboratories, you'll find over the course of your career that you're asked to solve problems that you frankly know nothing about, right? And one of the things about this field, I think that for me is really exciting, that you could just jump in. You just have to jump in. I have never yet found a case that that at a laboratory, and it doesn't matter which one, whether it's Los Alamos, Livermore, Sandia, you can always find somebody who knows something about whatever problem you have to solve. And that's really fun, So if you like doing things like that, if you like just kind of diving into new fields and trying to help solve problems, this is a great area for you. And so you have to use science tools to support the complex, to support the laboratories, to support the mission. You got to make infrastructure investments, right? And by infrastructure, I mean infrastructure writ large, right? You do have buildings, but you have scientific processes, scientific experiments, codes, hardware, and people. There's a huge investment, right, to do any of this stuff. So if you want to, run a code, right, on a large scale, now they're looking at exascale computing, but some enormous computer, you need people who can build the actual hardware, support it, run it, build the building that it sits in, build the cooling, which actually is now getting to be an increasingly large problem for these computers, is how the heck do you cool them down, right? And then the people who write the codes, who develop the theories that go into it, and so on. You just pull the thread, and it's an amazing string of people that you need to actually get this job done. Nuclear testing. So we're trying to do this mission of certifying and assessing and preserving an aging stockpile without additional nuclear tests. But as I said, we have a tremendous database of tests to rely on. And here's sort of a snapshot of all the different types of nuclear tests that were done. You had, of course, in the very early days, you have underwater tests. This was the first test series in 1946 after the war. You had airdrop tests, you had air launch tests, and then after you went underground in the early 60s, you had those types of, let's see, does this have a pointer on it? No, anyway, you had those tests with all kinds of cables and trucks in Nevada, just not very far from here, actually. And And then you had tunnel shots where they did effects tests, high altitude, the whole panoply, right? There was a tremendous test database, over 1,000 nuclear tests, which is essential to underwriting our understanding of how nuclear weapons operate. How did we do this during the testing days? It's amazing to think in the 1950s, for example, they were trying to diagnose these very extreme events, right? Talk about high energy density with a vengeance, you know, high pressures, high temperatures, very fast, right, in events in time. And they only had 1950s era technologies, right? They didn't have, you know, the high-speed digitizers and high bandwidth cables and stuff that you had even towards the end of testing, let alone what you might have today if you were using modern technology. So they had a lot of incomplete knowledge, is the bottom line, right? They would go fire something, they would get some results that came out of it, and then they would develop simplified theories because they didn't have computers. I mean, they did, but they were extremely primitive computers by the modern era. You know, far less than you have on your cell phone, right, nowadays. So they couldn't model things typically in great detail, and they came up with empirical theories of how these devices worked and then fit those theories to data, right? So they relied more, you know, and directly on nuclear test data because that was the, you know, that was the major leg in that tripod, right? That theory, experiment, simulation. That was, experiment was the biggest leg and the strongest foundation that they had for that. So based on the test database with empirical codes, you know, empirically tuned codes that they had at the time, they would, you know, they would assess things, they would field them, then deploy them, and there was a vigorous, you know, there's a whole huge national complex, right? They were constantly moving weapons in and out of the stockpile. The life cycle was, you know, 10 to 15 years typically. They weren't trying to preserve things over many decades. So, you know, if issues came up, they had a constant stream of devices going in and out of the stockpile. And the confidence was bolstered by the size of that stockpile, which was, you know, could be quite large, certainly in those days of the 60s. So that was sort of the milieu in which the whole enterprise operated. Really until the end, largely that, I would say that way of looking at things and way of doing business, you know, lasted till the end of testing. So we're really trying in this whole stockpile stewardship program over the last 20 years, trying to do something very different, right, with it in a very different way. What did you learn from testing? It's kind of amazing some of the things that one could learn from testing. I mean, you think to yourself as a designer who was one of my, you know, mentors when I was early in the program, said, you know, it's amazing that, you know, you're doing it, you're blowing up an atomic bomb. It's not like a very nice environment to try to understand things, right? It's hard, right? So, but it is amazing what you could glean from tests. Here on the right is a typical underground diagnostic rack. But this is sort of standard for what was there at the end of testing. And so you would take this rack, as it was called, and this rack held space for a lot of experiments. And you talk to the experimental physicists at the laboratories, and it's always fun because they would fight very hard for rack space. Rack real estate was precious, right? And they had huge arguments over it, right? You know, you're taking too much. No, you can't have it. I want to feed, you know, field this, field that. And so there was, you know, was not a lot of real estate available, so there were tremendous fights over who got what. But you could see there were different experiments that were fielded, and you see all the cables and the diagnostics that are fielded up and down the rack. And the bottom line is this is all based on the principle that the nuclear device emits various types of outputs, right? Neutrons, gammas, and X-rays. So you can look at those. Those carry information about how the device functions. And so then you measure those with various experiments which had line-of-sight pipes, detectors, cables, and so on and so forth, and then sent all of that stuff back up to those trucks that you see, you know, you saw in the previous picture way out there, out in the middle of the desert. There were another main diagnostic was radiochemistry. Here you can see some of the stemming in the hole. There's where the blast is. It's not so easy to see, but it's hopefully a little bit clearer in my slides. And then, you know, they would drill back, and then they would pick up, you know, debris there, and they would analyze that. and to try to make also further inferences about what was taking place in the device. So it's an irreplaceable set of data that's still out there, but I just want to emphasize that it's also, data that was gathered with the technology of that day, right? And if you try to, it's a little bit easier probably for me than for many of you, but I can remember 24 years ago, right? And you think, oh, geez, there's no internet, no cell phones. You were happy with your Apple IIe, or I guess there were early Macintoshes in that time. So, it was just a very different world to the technology that's available in modern times. Right, so how did you use all this stuff? So it's actually kind of a complicated cycle of work, right? And when you had nuclear testing. So if you were going to design a weapon, how would this happen? I mean, this is kind of a schematic flow of how that happened. You typically have some requirement that comes down. So the military says, we want something, and it's got to be such and so size and can't weigh more than this, and it's going to fit in this delivery system, and here's the performance we need of it. That's one very typical way. So you would have early development studies. You would try to survey the design space. What are the options for that to meet that particular requirement? And that's when you get the conceptual part, right? So you say, well, okay, I think this might be some way of trying to meet that requirement, sort of a notion system design. Then you put it into a computer typically. Now this is a very designer-centric perspective. After you think about it for a while, put it together, you make up a computer model of your concept. And then you start to go through this cycle here where you take your computer model, you subject it to design, simulation, analysis, you try to understand it. Then you go do a lot of non-nuclear tests, which then feed back into your computer model, because typically you find out your computer model is wrong in some way and you have to adjust it on the basis of data. And then you iterate, right? And then you explore computationally how is your system performing, right? And then by the way, it's a creative endeavor, right? It's different. Doing this sort of thing is different from kind of doing pure physics when you say, okay, I think Mother Nature acts this way, right? And I'm going to think very deeply about how does Mother Nature act. This is more like, how do I make Mother Nature do what I want Mother Nature to do, right? How do I put something together that will do what I want it to do? And what are the pitfalls in that? And then so you go through this iteration for a while, and then of that, some subset of that design would go then to nuclear testing, right? And if the nuclear test would do two things, typically go back up on that loop, and you would gather more experimental data from that test, and you would iterate and bring that information back into the earlier part of the design. And if it looked promising, then some subset of nuclear tests would be taken into a further stage, a weaponization stage. And then ultimately, some subset of that would be deployed in the stockpile. So there were a large number of things conceived, very large number of things conceived. Some subset of those things were taken to the point of a nuclear test. Some subset of those things that were actually tested were weaponized. Some subset of those things were actually deployed. So you have this kind of winnowing process as you go down before you get into the stockpile. And then I didn't even put the part on the other end, which is how do you take things out of stockpile? But there's a whole sequence of doing that as well. There's a whole dismantlement sequence. So there's really a lifetime. But that's how it was done during testing. And the issue is as we try to take the stockpile into the future, for many years into the future, there are a lot of detailed questions that we have today. And in fact, the fact that we can make such detailed computer models of devices today has itself provoked people to ask questions. And those questions don't have answers that can be found very easily or at all in the extant nuclear test data that we have. And so what do we do with that, right? We have to, there's no free lunch in this business, right? There's a conservation of information. You can't fabricate information. If you're lacking some information, you've got to find some other source of it. And that's where the big facilities that I'll mention later on, facilities like NIF and Z and Omega and DART and so forth, that's where they really come in. You try as best you can to develop experiments, because really experiment is the foundation, right? You know, experiment, everything has to be brought to an experimental test if possible. But you try to develop experiments that will yield at least some light on the question that you're interested in, right? And that is a very difficult synthesis to make, because you really got to look across all of your legs of theory, experiment, simulation, and put it all together, weave it all together into a narrative as what's going on. And now, since we don't have the direct nuclear test, we have to add in more margin, right, to account for uncertainty. So we're actually spending a lot of time in the whole complex trying to actually assess what are our real uncertainties. How do we account for that with more margin in these systems? And so that leads to kind of the new workflow, I would say, which is very much like the old workflow, except here you kind of replace the nuclear test with improved understanding, improved determination of your uncertainties, and greater margins, right? So that's kind of the challenge for us today, is how we steward the stockpile. And since we have to do it always within a finite budget of not only a financial budget, but also people budget, resource budget. You know, the greatest budget that each of us has is what we can do in our head. It's our attention, right? Our cycles to study something. That's always finite, right? You can only work yourself so hard. And so the whole enterprise has to work within this budget. So there's big arguments today, just in the same way that experimental physicists back in the testing days used to argue over rack space. There's huge arguments over shots on NIF, for example, shots on Z. There's big argument over computer time. Actually, that's one of the, so now I'm a manager, right? And one of the biggest arguments I always have to adjudicate is I got people screaming at me for computer time, right? And again, you just get these, you get these arguments over what's the priority and why. And that's really a reflection of thinking, right? We're all wrestling with this problem. How do we do this, right? And what are the things we really need to do? What are the most important priorities on the machines, whether they're computational hardware or whether they're experimental hardware or what. So, I mean, the advanced computing cannot be underestimated. It is just nothing short of stunning, the advances that have been made in computing over the past 20 years. I ran my very first weapons calculation. I was sitting in office with Paul Bradley over there at the time. Ran my very first one on a Krell, right? And not like a Krell you had today. I mean, it was, a single processor. It was kind of a nice machine in a lot of ways. But it was, just had nothing in terms of computing power compared to what you have today. You just could not. It's just hard to imagine. And Moore's Law, right, is really a stunning thing. When you live through Moore's Law for 20 years, you're like, oh my goodness, right? Now we're putting, billion zone calculations on the machines, and that was just inconceivable 20 years ago. And you can actually look at things in 3 dimensions now. You can look at things in highly resolved detail. But the one thing that hasn't changed, and I want to make sure to communicate this to you, is that the codes are not always perfect, right? They do lie sometimes. And again, as one of our senior designers often likes to say, says your job is to figure out when and where the code is lying to you, right? And that's the essential role of experiment, right? And experimental validation for these codes. But the codes are just tremendous. It's one of the biggest and most impressive success stories, I think, of stockpile stewardship that we should celebrate. And they just look to keep getting better and better. The machines, as I say, now we're looking at exascale machines, and it's mind-boggling to think, what that increase in computational power has done for us. So you have to integrate these things again in with improved physics models, right? Because now really so much depends on the technology. When you have that kind of computational technology, it actually opens up a whole class of theories now that you might want to put on the machines that were just impractical before, right? People thought about many theories and just rejected them, said there's no way I can fit this thing on a machine with any finite, and run the problem in my lifetime. But now you can run the problem, not only within your lifetime, but sometimes in a fairly short time. So that's really affecting also your fundamental theoretical research, right? It affects your model building. It's, again, if I can emphasize one thing for you guys, that this is a very integrated process, right? You have to know and be willing to touch on kind of everything, right? You have to look at what's your practical application, what's the computational power you have, what's the experimental facilities that are available to you, how do you tie it all together in one narrative? That kind of helps you plot out your work to attack a problem. I've emphasized, hopefully many times, I can never emphasize it enough, how essential experimental checks are on your theory. Humans are storytellers, right? That's one way to think of it. That's the way I like to think of it. And we will tell stories regardless of whether or not we have information to base those stories on. In fact, the less information we have, the wilder story we'll often tell. That's just the way we are. You know, there's no way around it. Don't even worry about it. That's just the way it is. But you have to compensate for that. And you have to have some discipline in terms of doing that. And the only discipline in the end of the day that really counts is Mother Nature. She doesn't tell any stories at all, right? Except one story, and that's how it is. So, you know, to have to, you know, to spin these great stories. And the other thing you notice, hopefully when you look at yourselves, you'll notice this in yourselves too, but with your colleagues, your friends, your academic field, whatever. Once people start to tell a story, they start to believe it, right? So this is another piece of advice, right? Never tell your own PR so much that you wind up believing it, right? But you will. And I've seen whole communities of people where we've convinced and I've been part of them, you convince yourselves this is the way things are going to go, and then you try the experiment, and the experiment says that's not the way life works at all. And so you've got to learn to celebrate, you know, that a good friend of mine from Livermore, you know, said to me once, he said, you know, one of the great things about these experiments is that they not only tell you you're wrong, they rub your face in how wrong you are, right? And that's very important. It's very important. So, you know, if you're looking at high energy density physics systems, for example, and you're trying to do an experiment on NIF, say, right, you've got to worry about how do you build the experiment you're doing, how are you modeling it, how is the diagnostic working, and is that system that you've put together really working the way you think it is? And I think John Edwards talked to you guys yesterday, was that right? And so, you know, he's running the ICF program over on NIF, and you know, that program is a great program and full of instances where you know, in real life you tried to do something and Mother Nature said, no, it's not working this way. You learn, you pick yourself up, you dust your knees off, and you keep working at it. Okay, so that's really, and that's also a lot of fun, you know, grappling with those mysteries, right? You know, just grappling with a recalcitrant Mother Nature is really one of the most fun ways as a scientist, you know, to spend your career, and one of the most humbling and instructive ways as well. In addition to high energy density experiments, this is where I kind of came from, so I very much enjoy that. But there's a whole other branch of experiments that one has to do to understand nuclear weapons performance, and those are done at places like DART. You can see DART is dual axis radiographic hydrodynamic test facility. Hydrodynamic tests. You're blowing things up and you're imploding things, and you're analyzing them. Here are the dual axes of DART. So you've got, you know, an accelerator on each axis, and you're taking pictures of the assembly and trying to understand the dynamics of that assembly from two different angles and at multiple times. This is kind of absolutely essential for getting at confidence in many things. It's bread and butter type of work for the nuclear weapons program. We do these types of hydrodynamic tests all the time. They're very expensive tests. They're big tests. They take a lot of time. Typically, they take too much time, in my view. That was an editorial comment. You know, typically, if you're really rocking and rolling, the time from concept to experimental data is about a year, right? That's moving pretty fast, and that's involved for getting all of the reason it takes so long is because you got a lot of complex parts that have to go together to do a hydro test, and that's things like, scheduling on the machine, getting the assemblies built, doing the design, going through the iterations to understand what you're going to fire, getting the diagnostics right, and so on. And it's a lot of effort to get that many people and that many different parts kind of moving in the right direction. That's one of the things that also just to communicate to you guys, the labs they do a lot of great benchtop science, but the national laboratories, especially the defense laboratories, are really kind of big science laboratories, right? This is why you pay, each of them has budgets, in the $1 billion range and above. And this is why the country pays that much money for these types of enterprises, is the big science. You need all of these people, all of these facilities, all of this equipment to do this type of experiment. But big science is also big in time scale too, right? And it's a big endeavor. It's a complex endeavor. And a hydro test is a great example of that. I just wanted to put up a few of the, a couple of the traditional diagnostics. Actually, this is the traditional diagnostic. It's a pin dome. You had these little electrical pins, kind of a little hedgehog type of thing, porcupine kind of thing there. And you'd use that, they would short out, and that would diagnose something about the implosion. These shots are rapidly being, this diagnostic, I would say, is relatively rapidly being replaced by optical velocimetry techniques that are becoming the norm and that are giving, again, a tremendous amount of data that was never available previously. A colleague of mine from the Department of Energy, I think, phrased it very aptly when he said, these optical velocimetry to pins are as high definition TV to Morse code, right? That's the kind of dynamic range you're getting in the modern diagnostics. It's really quite remarkable. And I was talking for a minute about large-scale science, and this is just sort of a summary of some of the facilities that are supported throughout the laboratories. Of course, we have the National Ignition Facility here at Lawrence Livermore, the Z Machine at Sandia, DART, and Lance, the Los Alamos, Omega up at Rochester, and then there's a whole raft load of computing centers all over the place. And as I say, one of the interesting things for exascale is the infrastructure for these computing facilities is now getting to be a big deal. So how are we going to cool these things? And that'll be interesting to see how that problem is solved. Last but not least, or getting towards the end, certainly not least, is the people, right? And we have people here. We got a great group here of new scientists that hopefully some of you are going to come into the program. But there's, again, that's just the tip of a very large iceberg. And one of the things when I was at Z, one of the great privileges at Z was walking through an experiment and realizing how many people were necessary to get one of my experiments fielded. It was very humbling. You'd walk through and you'd say, okay, who's doing the center section in the machine? You talk to the guys who were refurbishing the center section every day. You talk to the people who's making my target, right? So you had to go find the machinist who was actually making your target and thank them. Also, always thank people, right? If they're working on your experiment, be very nice. Bring burritos and things like that. You'll get an unreasonable amount of work out of people just by doing simple things like that. But it was 150 people at least. That was my rough estimate. Who were required to make one Z experiment that was all about some idea I had in my head and then put on a computer. So you need all of those people, and every laboratory has those people from the scientists all the way through the various technicians, and they're all essential, right? They all do a role that no one else can do, and if you don't have any one of those roles, the whole thing will just fall apart miserably, right? So you have to invest in those people. And I think that's something that we in the complex have learned painfully sometimes over the last 20 years, right? That when you're reducing size and worried about budgets and so on, you can never take your eye off the ball with the people, right? And they're very easy to lose. So So this program is one of many efforts to try to make sure that we're retaining, not only retaining people really, but bringing new people into the program and bringing new people into the exercise and keeping that lifeline healthy. How we're moving our way of doing business is another way of saying this is how we're moving our way of doing business from the end of testing in 1992 to, let's say, to pick a time, 2025. And here, you know, we had a huge part of the confidence was underwritten by nuclear tests, direct nuclear tests. You had designers with test experiment and so on, and then local experiments, calibrated simulation. Now we're moving over to designers who have not done nuclear tests. I never did a nuclear test. I was still in school when the last nuclear test was conducted. I knew and was taught by designers who had done underground testing. And I think I met only one or two people who had actually ever seen an above ground test. And they're gone now. And most of the designers, almost all the designers who did underground testing are certainly retired. You still get several of them that come by, you know, to impart their wisdom. But mostly now we haven't done nuclear tests directly, and that's just the way it is, right? And so now the simulations have improved and occupy a higher part of our effort. We've got the archive data. We've got high fidelity AJAX. You can argue about the relative size of the boxes. I don't want them to really be taken in any literal sense, but that's basically how we're moving away, right, from in terms of the stockpile stewardship effort. Right. So this is still an exciting program. It's a fundamental program, in my view, and the view of all of us who work in it for the nation. We have exciting scientific challenges and an important job. And we can make a lot of great decisions. We can do a lot of great work. But if it's not sort of fundamentally rooted in the science of what we're trying to do, then it's going to be on shaky foundation. And so that's why we always, again, have to come back to those three things, you know, theory, experiment, simulation. Those have to be rock solid if we're going to keep the deterrent of the U.S. In solid shape moving forward into the future. And hopefully, you guys are going to be part of that. You're already part of it now, and hopefully you guys will continue to be part of it as we move into the future. So that was it. I'd be happy to take any questions that you might have. Thank you.